So this is EE 619. We are at lecture 3. So let me start by quickly revising the transistor equations that we derived in the last class. So if VGS is lesser than the threshold voltage VTH, what is the region of operation? Cutoff. What is the current? So the drain to source current is equal to 0. Now, if VGS is greater than the threshold voltage, and if VDS is lesser than VGS minus VTH, what is the region? This is in linear or triode region. And the current equation is then given by mu n COX W by L into VDS into VGS minus VTH minus VDS by 2. Okay. And if again VGS is greater than VTH and VDS is greater than VGS minus VTH, what is this region of operation called as? Saturation region. What is causing the saturation? The channel is getting pinched off, right? So I'll denote that here. And the current IDS then becomes equal to half mu n COX W by L into VDS, VGS minus VTH, the whole square. Okay, so we have derived the equations. In this derivation, we know that we made some assumptions. So the actual thing happening within the device is going to be much more complicated than what can be captured in these equations. I'm going to take a step back and I'm going to give you an intuition as to why these equations make sense. So this is a very, very simplified intuition, and it's only to give you a feel for the current equations. It is not technically completely correct, right? So to do that, let me first take a block of material. So let us assume that some steady state current is flowing through it. Okay. So now let me also consider a small sheet in this. And let's say the charge in this sheet is Q. So Q is basically the charge density across this dimension. Okay. And if this is moving with a velocity V, what can I say about the current? So you basically have to look at how much charge is moving through this cross section per second. What would be the current? It will be Q times V. This is okay. So this Q is now charge density, right? So this is Coulomb per meter, and then you have velocity, which is distance per time. Right? So dimensionally also it is free. Okay. So now with this in mind, we are again going to look at our transistor. I have my gate node. Let's say I ground both my bulb and I pick one of these nodes and ground it, and I call this as source. And this is my drain. Now we are applying VGS at the gate node and VDS at the drain node. Let us start with a scenario where VGS is equal to 0 and VDS is also equal to 0. What will you observe? No current. Is there a depletion region that you will observe? So if you look at this junction, right? So this is basically a PN junction, correct? The substrate is P type. You have a diffusion region here, which is N plus. So you have a PN junction. And because of this, you will have a depletion region around this. Similarly, you will have another depletion region around this. Okay. Should I be showing the depletion region within the N plus region? So that is heavily doped. Therefore, the extent of depletion region into this N plus region is going to be very small, which is why I'm not showing it here. But there still exists a depletion region within the N plus region. So now, as you increase your VGS, you will have a depletion region being formed under the channel, formed under this gate. And then you will also have a channel forming under this. Okay, so this is for VGS greater than VTH, and my VDS is still equal to 0. Now, as I increase my VDS, what do you expect to see? So one change you will see is that the depletion region around the drain is going to increase. What else? What will happen to the channel? Channel will start to taper off. Because the charge density as you go across this length, this is the x direction, as you go in this direction, we saw that the charge density was equal to minus COX into VGS minus VTH minus V of x, where V of x is the voltage at a particular, at the point x in the channel because of the VDS that you have applied. So as your VDS is increasing, your channel is going to get tapered. Okay. So now this is basically linear region. The channel has not pinched off yet. So now let us assess the current equation based on what we derived earlier. So now the I is going to be equal to Q into the drift velocity. Again, this is a very complicated operation that is happening under the channel because this QI is a function of X. Therefore, this VD will also be a function of X. So we will simply look at how the current is varying closer to the source side. Because if there is some current that is flowing in this direction, the same current has to be flowing throughout the channel. Why? Because under steady state, if the current entering and current leaving were different, it would mean that there is charge accumulation occurring in between the channel. Then it is not steady state anymore, right? So if a constant current is flowing, that is if you are considering steady state conditions, the current flowing should be equal throughout the channel. Okay. So now if I increase VGS, what happens to QI? It will either increase, decrease, or remains the same. We have three options. I'm hearing only increase. How many of you are saying it should decrease? Okay. How many of you are saying it should increase? So it turns out the answer is it will increase, right? Because dq is a function of VGS. So if you increase, so basically the charge at this node, this will remain a constant irrespective of VDS, right? Because V of x here is 0. So as you increase your VGS, the inversion charge available is increasing. Therefore, your current is also expected to increase. What happens if I increase my VDS? What comment can you make about the electric field in the channel? It will increase, right? So if the channel length is L, on an average, I can say that the electric field will be equal to the applied lateral potential divided by the length. So if I increase the VDS, the electric field will increase, which means that the drift velocity will also increase. Okay. Therefore, you can expect the current also to increase. So if it's in linear region, you increase VGS, current increases. You increase VDS, current increases. Now, as I keep increasing VDS, what happens to the channel? It tapers more and more, and eventually we will hit pinch off. Okay. So let me exaggerate this a little bit. And let's say the channel is pinched off here. So now the new length of the channel is L dash. Okay. As before, we will assume that this L dash is very, very close to L. So basically, we are right now assuming that the channel length has not changed much. What happens if I increase VGS? The inversion charge increases, so you can expect the current to increase. What happens if I increase the VDS now? What is the drop across the channel? So this node is at 0 volt. What is the potential at this node? This is VGS minus VTH. Now let's say I increase VDS a little further. So it is going to get pinched off here. What is the potential at this node? Same. It is still VGS minus VTH, which means that if we assume that the channel length is not changing much, and from the figure, you can see that the potential across the channel is not changing at all. Therefore, the electric field in the channel is not changing much, which means the drift velocity is not going to change and your current will remain constant, which is what we obtained earlier, right? In this expression, we do not have a VDS dependence because, as I showed here, the electric field is roughly remaining same. Is this okay? Now, like I said, this is a very, very simplistic view, but I hope this has given you an intuition for this. Okay. So now we saw that the length of the channel is changing a little bit as you change VDS, right? So the channel length is now, it is a small change. So basically your channel length is getting modulated. So as circuit designers, we like to keep everything simple. So we call this phenomena as channel length modulation. Because the channel length is now getting modulated as your VDS increases. So now let us get back to this intuitive picture again. Now let's say as I increase my VDS, the drop across the channel is remaining same, but the length is it increasing or decreasing? It is decreasing. Then what should happen to the drift velocity? Drift velocity should increase, right? Because the electric field has now increased. Same potential across a smaller length. So the electric field has increased. Therefore, you can expect the drift velocity to also increase, which means we should technically see an increase in the current. Is that okay? Intuition is fine. Now let us get back to the derivation. So if you remember, when we derived the current, the original expression that we got was half mu n COX W by L dash into VGS minus VTH the whole square. And then we said that this L dash is nothing but some length minus delta L. Now in this expression, I have a factor 1 by L dash. So let's see how we can simplify 1 by L dash, right? So this is equal to 1 by L minus delta L. So now the same old, I take L outside. So this becomes L into 1 minus delta L by L. What do you see something, what do you do when you see something in this form? You do binomial expansion, take it to the numerator and you get 1 plus delta L by L. Now tell me, is this delta L, let's look at this factor delta L by L. Is this going to increase or decrease as you change VDS? This is going to increase, which means this is proportional to VDS. Now I'll replace that proportionality constant. We'll put a proportionality constant as lambda. Okay. So now let me substitute it back into the equation. My IDS is now equal to half mu n COX W by L into VGS minus VTH the whole square into 1 plus lambda VDS. Should lambda be positive or negative? This has to be positive, right? Because what was our intuition? As VDS increases, we expect the current to increase. So it turns out for that to happen, lambda has to be positive. So this is positive. What is the unit of lambda? 1 by volt. Why? Delta L by L is unitless, which means lambda into VDS has to be unitless. Therefore, lambda has to have the unit per volt. This is okay. So now this lambda is actually an empirical parameter, right? Now, all of the equations that we derive, we would like everything to have a physical background. But sometimes trying to express that physics in terms of equations will result in very, very complex equations. That makes it really hard for us to do computations or as designers to have a feel or intuition for the circuits. So in such cases, what we do is we do a lot of measurements, we get measured data, and then we tweak the lambda parameter such that the measured data will fit with the equations that we have. So this is what we call as an empirical parameter. Now, the equations that we are going to deal with from now onwards is actually semi-empirical and semi-physical in nature. There is a physical background for most of it, but wherever it is getting complicated, we do this empirical fitting. The problem with this empirical fitting is that the results you get are valid within a certain region. Like for example, here we deal with COX, right? COX is epsilon OX by TOX. Now, if I change TOX to any value, provided I know the exact values of TOX and epsilon OX, I can calculate the COX exactly. But for parameters like lambda, the fitting has been done under certain conditions. So if you change your temperature by a large amount, or if you change the width or length of the transistor by a very large amount, then the results you get based on the equations that have empirical fitting need not match. So when you're dealing with equations like this, you have to be also aware of the situations under which the equation is valid, right? So now, when we get these model files, basically we will get the model files of all these transistors from the foundry. Usually the foundry will also tell you what are the conditions under which you can use these model files. And you have to follow it. Otherwise, what you design and what you finally see after fabrication will not have the same current value or same performance. Okay, so now let's move on. So we have done channel length modulation. So the next effect I would like to discuss is called as body effect. Okay, so what is body effect? Have you heard of this term before? What does it mean? So the threshold voltage can change because of what? Because of the voltage applied to the body. So again, let's start with an intuitive feel, then I will give you the exact equation. So originally we had grounded our source. We also grounded the bulb, and then we applied a gate voltage and a drain voltage, right? So for this discussion, let's assume that the drain voltage is also 0. Now then you have a depletion region under the channel. And then you will also have some free electrons under the channel. This is of course assuming that the gate voltage is greater than the threshold voltage. So now let me introduce. So let's make the bulb voltage more negative. What comment can you make about the depletion region between source and bulb voltage? Between the source and the bulb, what comment can you make about the depletion region? Is it going to be wider or smaller? It is going to be wider, right? So now here's the thing. So you have electric fields starting from the source side that has to end at negative charges on the bulb side, right? Now there are two ways this can happen. One is to actually deplete the ions there, deplete the atoms there, or now you have mobile carriers here. And so some part of this mobile carriers will come towards this region, which means now if you want to have the same level of inversion charge, what should you do? Should you increase the gate voltage or decrease it? You have to increase it, right? So effectively, to get the same amount of inversion charge, you have to apply higher voltage, or your VTH is now increasing. So your VTH is increasing, when your VSB increased. Okay. So again, this is a very simplistic view. Those of you who are interested in learning actually what happens, please do take a device physics course. So let me give you the equation for this. So your VTH is now equal to VTH naught plus gamma into root of psi s at VTH plus VSB minus psi s. So the psi s is basically 2 phi f. I'm writing it as mod psi s because for NMOS it doesn't make much difference. The value is positive. When you finally deal with PMOS transistors, the psi s value is going to be negative. Hence the mod sign. So this VTH naught is the threshold voltage for VSB equal to 0. Now this VTH naught is also an empirical parameter because the actual threshold voltage is a function of so many things. So in class, we saw that it was a function of psi s, depletion voltage, COX, etc. In fact, it also depends on the work function of both the metal and the semiconductor, depends on the impurities that got trapped at the interface of the silicon dioxide and the semiconductor, and a lot of other manufacturing processes. So again, we do empirical fitting to get VTH naught. Gamma is called as body effect coefficient. So now can you tell me whether this gamma should be positive or negative? Why positive? Right. If VSB increases, our intuition was that VTH has to increase, which means when VSB is increasing, gamma also has to be positive for our VTH to increase. Okay. Again, now tell me the units for gamma. So what is the unit for VTH naught? This is volts. This means this whole thing has to be volts. So this has a dimension of square root of volts. Therefore, gamma should also have square root of volts. Is this okay? So now let us move on to what happens as you make your channel lengths smaller and smaller. So let me give you an intuition behind why we should worry about short channels separately. I'm going to exaggerate and draw a long channel. Okay, now let me draw a short channel. Let me also mark the depletion regions around the source and the drain. What do you notice first? So the definition for short channel is this. A channel can be called as a short channel when the width of the depletion region and the channel length are comparable, are in the same order, right? So for long channel transistors, this depletion region is a very negligible part of the channel length. Whereas for short channel transistors, they are very much comparable and is a significant part. So now this is going to result in a lot of different interesting properties in the transistor. So one quick thing that I can tell you is this. So in applying a gate voltage and trying to invert the channel, we first had to deplete. We had to first deplete the region under the gate. and then had to get the inversion layer, right? But in a short channel, part of this is already depleted because of these depletion regions. That should mean that the threshold voltage you require should be lower, right? The other part is when you apply an electric field. So the electric field here can now affect the electric field near the source end also, because they are now very close to each other. Now, another interesting factor relates to the drift velocity. What comments can you make about the drift velocity of electrons in short channel? Is there anything that you can say? Drift velocity is very high. Okay. So why do you say that? Right. So that answer is partially correct, right? So as you said, when the distance is small, you would expect the drift velocity, the electric field to be higher. So a small part here is that as you keep reducing your length, you would keep your VDD also to be small, right? Because if you apply the same level of VDD for small channel lengths, breakdowns can happen. So your VDD also reduces. For example, at 180 nanometer, the typical supply voltage is 1.8 volts. For 130 nanometer, it became 1.2 volts. Now at 65 nanometer, from 1.2 volt, it went down only to 1 volt, right? So the supply voltage is not scaling exactly by the channel length, which means that you can still expect to have high electric field as you go down, right? Is that clear? Your supply voltage is scaling, but it's not scaling with the same ratio as the length. Therefore, the electric field you will see in the channel is going to be higher than that you see in the long these transistors, long channel transistors. Okay, now that said, I am now going to plot drift velocity versus electric field. Would this keep increasing like this? Right, what happens? It is going to saturate. So after a particular electric field, which we call as the critical electric field, this is now going to saturate, right? So now I can model my electric field. Sorry, I can model this VD as equal to mu into electric field when my electric field is smaller than EC. And the drift velocity, we can say that it saturates to a particular number. So VD is equal to VD sat when the electric field is greater than the critical electric field. So now I have to include this information in our current equation, because if drift velocity is saturating, it should mean that our current is also going to saturate. Now here is the problem. We are circuit designers. We don't want to deal with drift velocity, electric field, etc. We want to be dealing with currents and voltages, because that makes it easy for us to design things and also to focus on circuit related problems, right? Not related to charges and electric fields, etc. So now how do I do that? So we will relate this drift velocity, the saturation drift velocity, to a saturation voltage, right? So I can write the electric field in the channel as the drain to source voltage divided by length. Okay. Which means this critical field, now I can write it as some VD sat divided by length. So if the voltage I apply is equal to VD sat, that means that the drift velocity has saturated. Is that clear? So instead of focusing it in terms of VD sat, now I have a corresponding voltage. So if the VDS I apply is greater than or equal to VD sat, I know that the drift velocity has saturated and the current has also saturated. Is this okay? Okay. So now let me plot the current. ID versus VDS. So I'm going to do this for two cases. In the first case, I'm going to take a long channel transistor. Right? If the transistor is long channel, what comment can you make about its VD sat? Is it large or small? Right? Because VDSAT is now proportional to critical electric field into length. So if I take a long channel, my VDSAT will also be larger. Okay, and it has a particular W by L. The length is large, but W by L remains the same. So for example, I could be looking at numbers like 200 nano, 2 micro by 1 micro. Okay, so how does the plot go? It will initially start in the linear region. Then it will hit the voltage VGS minus VTH. And then it will enter into saturation region. Okay, so now I'm going to take a short channel device. So let's say the W by L is 200 nano by 100 nano. So the W by L is same, but the channel length is short. So what comment can you make about the VDSAT? Right. So I will have a small VDSAT, which means this VDSAT now could be smaller than this VGS minus VTH. Okay. So now the current is going to increase linearly till this point, and beyond this point, the current is just going to saturate. Okay. So now I want to find the value of this current under saturation. Can you recommend a method? Plug in VDSAT into current equation of which region? Linear region, right? Because if I plug in VDS equal to VDSAT for this point in the linear region, because we want the plot to be smooth, right? So you plug in the value of VDS equal to VDSAT in the linear region equation, right? And we know that that current will remain the same throughout. So can you tell me the equation for current? Mu n COX W by L VDSAT into VGS minus VTH minus VDSAT by 2. That's it. So now what are the conditions under which you get this current? First part is VGS has to be greater than VTH, because of course we want the device to have an inversion layer. What next? VDS has to be greater than, VDS has to be greater than, if VDS, okay, let me write that. VDS has to be greater than VGS minus VTH. Any other condition? Condition for which you get this current. We are writing for the velocity saturation region. It has to be greater than or equal to VDSAT. Because if I simply write VDS greater than VGS minus VTH, it is pinch off saturation. Right? Now we have one more constraint, right? We need to know the relationship between VDSAT and VGS minus VTH. Are you following? So we also need to ensure that VDSAT is smaller than VGS minus VTH. So now if you take a transistor, ensuring that it is in cutoff is very easy. You just have to check the VGS. But to check whether it is in linear region, saturation region, which is pinch off saturation, or velocity saturation, is getting slightly complicated, right? So which is why we now have to come up with a unified model to make our lives easier. Which one? In this equation, so we are writing the equation for the red curve, for the short channel MOSFET. So I'm taking two transistors, applying the same VDS, same VGS. So why do you say that the VDS has to be larger for the long channel? VTH. Okay, so we are assuming that the VTH remains constant throughout. Yeah. So first part of the unified model, we'll start with what we know. IDS is equal to 0 when VGS is lesser than VTH. Second part, so can you look at the three equations we have for the current? One is linear region, one is velocity saturation, one is pinch of saturation. Is there any similarity between all three? So mu and COX W by L is there. And we just saw that you can get the velocity saturation current equation by replacing VDS with VDSat. So similarly, if I could get the pinch of saturation current equation by replacing VDS with something, then we are sort of sorted. Can you look at the pinch of saturation current equation and tell me if there is some manipulation that we can do? If I put VDS as VGS minus VTH, I end up with this equation. Is that clear? Okay. So now, armed with this information, we will write our current equation as mu n COX W by L. Instead of writing VDS, VDSat or VGS minus VTH, I'm going to write it as V min. This into VGS minus VTH minus V min by 2 into 1 plus lambda VDS. Now I need to define what my V min is. I know that V min has to be one of the three values. It should either be VDS, VGS minus VTH, or VDSat. How should I choose the value? Should be minimum. So if VDS was the minimum of the three values, what region is the transistor in? It is in linear region, correct? Because if VDS is the minimum of the three values, which means you are operating in this region. Okay? Any questions? VDSat is a technology parameter that depends on the length of the transistor. And this is the length, this is the VDS for which you will have critical electric field in the channel. Okay? Correct. So I'll come to that in a minute. But other than that, is this clear? Is this condition clear for figuring out whether the transistor is in linear region, saturation region, or pinch off region? Is this clear? Okay. So now coming to this 1 plus lambda VDS. So in linear region, do you think there will be a channel length modulation? There is no channel length modulation, right? But our aim was to find a unified model, and lambda value is already small. In linear region, the VDS value is also small. So this factor will not cause much change to your expression. So for quick hand calculations, if you are comfortable, you can easily ignore this and do the remaining for linear region calculation. Is that okay? Now we also have to, because it is a unified model, let's also write the expression for threshold voltage. This is equal to VTH naught plus gamma into root of psi s plus PSB minus root of psi s. Of course, this is true when VGS is greater than VTH. So this is what we call as the unified model, and it allows us to calculate the current for an NMOS transistor very quickly. And it also allows us to identify the region of the operation very correctly. Any questions on this? Sorry? Gamma is negative for poles. We will come to the PMOS in a short while. So let's focus on NMOS transistor. Now let me identify some of the parameters. So we have mu and COX. We have lambda, this VD-SAT, VTH0, and gamma. So let me write down these 5 parameters. So mu and COX, I'm going to call this as Kn prime. Okay. So the parameters in this model are Kn prime, lambda, VD-SAT, VTH0, and gamma. Can you tell me the signs of these parameters? Kn prime is positive, lambda, VD-SAT, VTH0, and gamma is also positive. Okay. Now all of these are empirical parameters, which means they are fitted based on the measurement data, right? And this model consisting of these 5 parameters is what we call as the level 1 model. So this is the level 1 SPICE model, and this is useful for doing quick hand calculations and for developing certain circuit intuitions, right? Now clearly, this is not the complete picture. Therefore, if you want to actually design a circuit, like a circuit that you want to design and then fabricate, you can't solely rely on these. Therefore, the models that are developed by the foundry, by the device engineers in the foundry, are going to be much, much more complicated. So any guesses on what is the level of the model file that we are using right now for designs? So this is level 1. What would be the level? You can give a number. Level 40. 14. Okay. Any other numbers? Level 5. Okay. So it turns out we are using level 54 models. So this is a typical model file. So for example, for this NMOS, you can see that it is level 54. Any guesses on the number of parameters? The number of parameters can vary anywhere from 100 to 250, depending on how well it is modeled and what are the features that you want to capture. So if I can quickly scroll through this and show you that this is not a very easy business, right? The modeling things. But if we were to do a design by relying on these, as designers, we would be lost. We can use these model files for simulations. But as designers, you will have pages and pages of parameters and you wouldn't know what to tweak and how to tweak. Right? So which is why we have level 1 model for quick hand calculations. And for accurate results, you rely on the simulation. This is clear? So I can simply, I don't know how much intuition you will get by looking at this, but I can show you how complex the whole thing is. So you can see terms like VSAT. So these will be related to the resistance. Yeah. So this file, by the way, is available in Dr. Imon's website. So feel free to look for it. This was part of the high frequency analog course. It was uploaded for an assignment. Okay. So now here is another question. There is mu and COX and W by L together, right? Why did I not combine W by L along with mu and COX? Right, because W by L is now a design parameter that is under our control as a designer. So what are the design parameters for us right now? There is width, length, what else? No, TOX is not a design parameter. Mu and COX together has gone under the technology parameter Kn dash. You can control the voltages and the currents, right? So you can control VGS, VDS, VSB, and by controlling these, you can control the current. Okay. So now if you have to propose a solution for a problem that you have to implement a circuit, your solution should consist of tweaking these parameters. You can't come back and say that I will tweak a technology parameter, because then no foundry will be willing to fabricate it for you, because the foundries have taken several months and several years of innovation into figuring out a particular process and the process parameters. Okay? So unless you work in directly in a foundry or you're related to device fabrication, our focus is on how can we tweak these design parameters. Is this clear? Then let me give you a quick problem. You have to plot ID versus VDS for two cases. One case is where the lambda is equal to 0, that is channel length modulation is 0. Second case where channel length modulation is not equal to 0. Can you do the plot? You don't have to consider velocity substitution. So earlier when lambda was equal to 0, so your current increased till the point VGS minus VTH1, and then it had saturated. So this is when lambda is equal to 0. Now what happens? There is no difference in the linear region. Once it enters the saturation region, the current is not constant. It is going to increase slightly with lambda. What is the slope of this curve? Slope of this curve is lambda. Okay. So now let us look at few other non-idealities that are more prominent in short channel transistors. So the first one is subthreshold conduction. So far, the one thing that we kept repeating was when VGS is lesser than the threshold voltage, the current is equal to 0, right? But from our initial analysis, we know that even when VGS is lesser than VTH, there are some inversion charges available. We call that region as weak inversion earlier, right? Which means if there is an inversion layer present, it is also possible that a current is present, correct? There is an inversion layer. If you apply a lateral electric field, you will get a current. Just that the value of the current will be negligible. So this current is given by the equation. IDS is equal to IS into e power VGS by n times KT by Q into 1 minus e power minus VDS by KT by Q into 1 plus lambda VDS. So is this current a good thing or a bad thing? Why is it bad? Sorry? But there is some current. Okay. So now whether this is a bad thing or a good thing depends on whom you ask. For example, if you were to ask a digital engineer, in digital designs, we use these as switches. So when it turns off, we want it to really turn off and not conduct anything. So this current is bad in such cases because it means that even when your circuit is completely turned off, it is consuming some power and your battery is leaking unnecessarily. Now, if you were to ask an analog engineer, you will get a slightly different answer. And the reason is this. If I were to differentiate this with respect to VGS, basically dou IDS by dou VGS, you get a transconductance. And this transconductance GM value is now an exponential function of VGS. Right? So dou ID by dou VGS is now exponentially related to VGS. which means you can get a higher value for GM. So there are designs where you would bias your transistor in the subthreshold region to get higher gains. So we'll not get into that now. This is a digital design course. So as far as we are concerned, this is a bad thing. So now if I were to plot IDS versus VGS, we earlier said that up till VTH, there is no current. But of course, now we know that there'll be some small value of current. Then it enters in saturation region where it is quadratic. Then it goes to linear region. So this is linear. This is saturation. So clearly, we can see the behavior of the current very clearly in the subthreshold region, correct? No, right? You can clearly see it because we have drawn IDS on a linear scale and the current values are much, much small compared to the current values present in the saturation and linear region. So what do? We plot it in logarithmic scale. So we do log of IDS with respect to VGS. Because it was exponential here, now it will become linear in the log plot. So this is going to vary linearly, and then you will have the quadratic region, and then finally the linear region. So now the slope of this curve is of interest to us. What would we like it to be? Larger slope or smaller slope? Larger slope, right? So how we quantify this is in the following method. Let's say I want my current to reduce by 10 times. How much should the VGS drop? Okay, so let me copy this equation. So I want the current to drop by 10 times. Let me call this as VGS1 and this as VGS2. Can you tell me what should be the value for delta VGS given by VGS1 minus VGS2? So please do the calculation and tell me what should this value. So you should get the expression as N KT by Q into ln 10. So the units for this is millivolts per decade, because you're calculating by how much you want to change your VG so that you can get a decade drop in the current. And this is represented using the parameter S called as the slope factor. So typical values at room temperature for the value N equal to 1 is around 60 millivolt per decade. And we would like this value to be as small as possible. That would mean that even for a smaller change in VGS, you are able to get a larger drop in the current. Is this okay? So moving on, now I'll quickly touch upon some of the other non-idealities. We will not get into the details. So the first thing is VTH roll-off with reduction in length. So as I explained slightly earlier, as your length reduces, the depletion region corresponding to the source and the drain will become significant regions of the channel. So part of the channel is already depleted. Therefore, you don't have to apply as high a threshold voltage as earlier. So another factor is called as drain-induced barrier lowering. Or in short, DIBBLE. So this is where the electric field on the drain side is beginning to affect the electric field on the source side also. And this will result in lower threshold voltage. Next, we have gate leakage. So far, we said that the gate current is 0. But as the thickness of the oxide reduces, which happens as you go to shorter and shorter channels, it is possible for you to see some gate current because of quantum effects such as quantum tunneling. And similarly, you will have substrate leakage. And then you also have something called as mobility degradation. Due to the vertical electrical field. So far, when we were looking at the current flow, we assumed that there is a lateral electric field. And because of this, the electrons are moving from source to drain. But we are also applying a VGS, which means there is a vertical electric field also present. So basically, the electrons are moving in a 3D space, which has both horizontal and vertical electric field. Now, because of this vertical electric field, the electrons will also move towards the gate, not just towards the source, right? So because of this, there is a reduction in the effective mobility, and this will change your current equation a little bit as well. But like I said, we are interested in being able to design circuits with an intuitive feel so that we know what parameter to change. We roughly know that if I change the width, how is the performance going to change, etc. For the exact result, we will rely on the simulation, which we can happily use the level 54 SPICE model. Is this okay? So then now we will move on to the PMOS. So first, let us look at how this PMOS is going to be fabricated on the substrate. We know that the substrate is common for all transistors. It is P-type. Now on this, if you want an NMOS transistor, you can create a source and drain diffusion regions as N+ regions, and then you will have the oxide and the metal on top of it. How do I get a PMOS in a P-type substrate? Okay. So you first make an N-well, and within this N-well, now you will put your P+ regions. And then you can have an N+ region to access the N-well. So this basically becomes your body. Now among these, one will become your source, the other becomes your drain, and you have the gate here. Okay. So now let's analyze in detail the PMOS transistor. So this is N-type. Okay, I'm going to assume that both the bulk and the source are shorted. This is source, bulk, sorry, I should call it as body. Because when I say bulk, we usually think of the substrate. So now if I say bulk for a PMOS transistor, please correct me. I should definitely call it as a body. And let's say this is my drain. So let's apply a VGS here. I'm going to refer all the voltages with respect to the source. And let's say VDS is initially 0. Let's start with VGS greater than 0. What will happen? What charges are deposited on the gate? Gate is positive. What should happen at the surface just below the gate? You should have electron accumulation, right? So again, this was an N-type material to begin with, and the surface has become more N-type. Therefore, what do we call this region? Accumulation. Okay, so now let's make VGS to be lesser than 0. What happens now? So you will have negative charges on the gate. This will initially deplete the region under the channel. So you'll get positive ions. And as you decrease the value of VGS, you will then get holes next to the surface. So all of this is happening for VGS lesser than 0. So as VGS reaches a particular threshold voltage, we say that the surface is inverted. And what does that mean? The surface is now as p-type as this body was n-type earlier, right? So if the doping concentration in this n-type region was Nd, as your surface concentration reaches the value Nd, we say that the surface has been inverted, and the VGS value at which this happens is called as the threshold value. So I will put a P here to denote that this is for the PMOS transistor. So is VTHP positive or negative? It is a negative. So now rest of the transistor equations, we can easily compare it with the NMOS transistor and derive. So I have a comment to make here. So you could be writing your IDS equations as a function of both VGS or VDS, and of course all the other parameters, or you can write your ISD as a function of VSG, VSD, etc. I mean, you can think of other combinations as well, but these are the two popular conventions in which we write the PMOS current equations. So now if you're writing it as a function of VGS, VDS, etc., then you will put the parameters such as VTHP as it is. Whereas if you're writing it as a function of VSG, then you will start to use the modulus of these parameters. Okay. Now, both of these conventions will give you the correct results. It is important that you stick to one and use that. Now, in this course, I will be following this convention because in E210, you would have learned this convention. And in E610, which is running parallelly to this course, you will again be using this convention. Okay. So now let's first write out the equations and then we will do the unified model. So for VSG, ISD is equal to 0 for VSG lesser than mod VTH. Okay. Now, if VSG is greater than mod VTHP and VSD is lesser than VSG minus mod VTHP, then we say that this is in linear region. For a minute, we will ignore the velocity saturation so that I can write out the equations without causing much confusion, right? And the current equation becomes UPCOX W by L into VSD into VSG minus mod VTHP minus VSD by 2. Okay. Similarly, I'll write out the equation for pinch off saturation. The condition, of course, is that VSG has to be greater than mod VTHP and VSD has to be greater than VSG minus mod VTHP. In all of this, I'm assuming that the VDSat value, the mod of VDSat value is very, very high so that we don't have to worry about the velocity saturation. Then the current ISD is given by half UPCOX W by L into VSG minus mod VTHP the whole square into 1 plus mod lambda P into VSD. Okay, so now tell me, in this device, what is the direction of current? Is it from source to drain or drain to source? The current is going to go from source to drain. What is the majority charge carrier now? Holes. So the holes are also going from source to drain. Our current is also going from source to drain. Now, if current is going from source to drain, which of the potential has to be higher, the source voltage or the drain voltage? The source voltage has to be higher. So current always flows from higher potential to lower potential. Charges are always going to go from source to the drain. Okay. Now, in an NMOS, what was the majority charge carrier? Electrons. The electrons were going from source to drain, correct? Which means the current was going from drain to source. So that meant the drain was at a higher potential. Now, in all of these devices, there is no difference between the source or the drain. Whichever is the higher potential determines which one is source and which one is drain. Okay. So now we have to write the unified model. So I'll quickly write this equation and then we can wrap up the class. So what would be the first part? ISD equal to 0. For VSG less than mod VT. Now the second part is ISD equal to UP COX W by L. You can call it as KP prime into V min VSG minus mod VTP minus V min by 2 into 1 plus mod lambda P into VSG. Where what is the value of V min? This is minimum of VSG minus mod VTP, mod VD sat P, and VSD. This is, of course, under the condition VSG is greater than mod VTH. And finally, the threshold voltage will change as VTP naught plus gamma into root of psi s plus VSB minus root of absolute value of psi s. So like I mentioned, in the other notation, the other convention of writing these equations, you wouldn't write mod VTHP or you wouldn't put mod VD sat P, etc. Now, which one? This one. It doesn't change in this. It is VSP expression. So for current equations, you can switch. This one, you can remember it as it is. So if you are more comfortable with the other convention, feel free to use it in the exams as well as in the evaluation units. So if your final answer is correct, you will get marks. If you do it correctly, you will get the marks that you deserve. So you can follow either of these methods. Make sure you're doing it right. That's it. So now here also we have 5 parameters. So let me quickly list down the parameters. So we have K prime, which is mu n COX for NMOS transistor, mu p COX for a PMOS transistor, then gamma, VT naught, VD sat, what else? Lambda. Now for an NMOS transistor, we saw that all of these are positive values. It turns out for a PMOS transistor, all of these are negative values. So K prime is basically mu p COX, right? Physically, it doesn't make sense for it to be negative. But the current definitions conventionally is written for IDS. So drain to source current is now negative in a PMOS. Therefore, in the simulation tools, K prime is negative for PMOS. So I think with this, we can wrap up today's class. And in the next class, we will look at PMOS, the capacitances in the MOS transistor. Thank you.